Guys, first I'd like to thank everybody for joining this webinar on our commercial air-to-water inverter heat pump. My name is Ken Eggleston. I'm Director of Sales for the Mestek Boiler Division and let's just say Hydronic Solutions at this point as we talk about this product. So first, I just want to tell you guys are all muted, so you're not going to be able to ask questions. But if you look at your taskbar there in the go-to webinar, you'll see you have the option of hitting question or chat. Please feel free to type in any questions you may have in either one of those, and our team here will try to respond to them as this presentation is going on. And afterwards, if there's a few left, we'll try to tackle them just by me answering them over this webinar. So that being said, I'm just going to get started here. Okay, just to start off, I just want to give a little history on Mestek as a whole. So Mestek is our parent company. It was established in 1946 in a rented garage here in Westfield, Massachusetts. We're now composed of over 40 specialty manufacturing companies. Our leading division would probably be our HVAC division, and then we go into our machinery division. We also have louver and dampers, architectural, and then we have our own control technology group. So the Mestek boiler group consists of 3 different companies, being ATH, Advanced Thermal Hydronics, RBI, and Smith Cast Iron. On the ATH, Advanced Thermal Hydronics side of things, we have the KN series, the KN series plus. So the KN series ranges from 200,000 BTUs up to 4 million BTUs at a 90% efficient. This is a condensing cast iron boiler. It's been around since 2004, and we have over probably 25,000 of these out in the field. The cool thing about it being from 2004, as long as I've been here at Mestek now 15 years, I've seen this boiler change and get more advanced as we progress through the years. So we're keeping up with the Joneses with this product. And then on the other side of it, we have this KN Plus, which is 96% efficient, and the sizes range on that one from 600,000 up to 4 million BTUs. Okay, this product does have a 25-year heat exchanger warranty, the leader in the industry. So the other company is RBI, and RBI started off as a copper fin type water heater boiler product. Those sizes currently range from around 500,000 up to 10 million BTUs. Okay, we have now moved into the condensing high efficiency stainless steel products, which range from 199 up to 6 million BTUs, offering water tube and fire tube products that can be used for water heating on the water tube side and boiler, and on the fire tube side, it's boiler only. And lastly, just the Smith Cast Iron. So this is our sectional cast iron boiler that can be used for hydronic systems and low pressure steam systems. So as we move into just touching on this air to water heat pump, I want to give you an idea of why we're moving in this direction. And really, as you guys have seen, if you've been watching the news or just checking on the way the US is moving, we are trying to reduce the carbon footprint or the carbon emissions in the US. So there's 3 critical segments that is focused on, carbon emissions, carbon reduction, and it's vehicles. So you're seeing those Tesla electric vehicles and a lot of the other manufacturers starting to follow suit. So that's happening. Your industrial processing of how we process things, we might be looking more towards a more greener way of doing that. And then our buildings. So in our industry, specifically heating and cooling. So the US goal is to reach net zero emissions by 2050. Okay, that's a long ways out, but I think we're going to see a lot of changes moving towards that 2050 that we're going to have to meet those goals and try to accommodate what's going on. So US goal for carbon pollution free power sector by 2035. So just a quick overview, and I'm sure there's more states out there that are moving in this direction, but just to touch on a few. You know, New York City is trying to do a 40% reduction of emissions. So they've already started this around 2005, and they will keep progressing from there. All buildings over 2,500 square feet, that's going to start in 2024. Your greenhouse reductions of 80% by 2050. That includes domestic hot water and HVAC systems, okay? And now they're throwing out some rebates on Long Island, which I'm seeing $1,000 per ton for air-to-water heat pumps. So that's going to help you with that upfront cost, and I hope a lot of states and cities follow in that same direction. California is going to be a huge electrification market, especially in the northern side of it. They got $1 billion approved for electrification out there. And so they're going to be moving to no natural gas on single family homes. That's new construction, but that is the way they're moving. So we want to take advantage of that as well. DC, they want to go carbon neutral by 2050. So that's a 50% reduction of emissions by 2032. Chicago going the same direction. They want to be carbon neutral by 2050, 50% reduction by 2032. And then New England, being Massachusetts, we're also working on getting clean energy. So their goal is to be 100% clean, renewable energy by 2035. Canada is also following suit. So they're now supporting homes and building and programs such as, you know, to reduce this carbon footprint as well. So they do have a climate action incentive funds. So they're trying to phase out the pollutions from coal-fired electricity by 2030. So they get rid of that coal-fired and probably move towards more of a natural gas to get their electricity. They're increasing their incentives to get renewable energy, increasing their investment in transmissions lines, smarter grids, trying to hit those rural communities and reduce their use of like fossil fuels, and putting a price on carbon pollution. So let's just say you had a building that's putting out more carbon than is allowed. There could be some fines following suit. I also heard they were talking to doing that in New York City as well. So these things are coming, and we just want to be prepared for it. So what is an air source heat pump? Okay, so just to kind of give you a rough idea, I think some of you, you probably have central air or some type of AC in your home, and how we change that hot air to cold air to condition our homes. It's very similar there. So we're taking that thermal energy out of that ambient air, and it will even do it at very, very low ambient temperature. So there's always some type of thermal energy in that air, and we're taking it out and we're pushing it towards a warmer area. In this case, water. So where we're taking that energy out of those coils, we're putting it into the water and gaining efficiency by doing that. And I'll get into that as we get into this presentation. So what's the value of an air source heat pump? More energy. It's more efficient than straight electric, and we'll get into that as well, what a COP is. It's more environmentally friendly, no harmful gases, and we're just looking towards more of a cleaner, greener solution against fossil fuels, and that's the way America is going. So feature and benefits, I already touched on that. Green technology, environmentally friendly. We have an enhanced vapor injection EVI inverter compressor, which I can get into a little bit. So just to give you an idea of what EVI is. So EVI is used to achieve a higher performance at a lower ambient temp. Okay, so the EVI is designed for cold climate heat pumps. And just to give you a quick rundown, it uses a third small internal plate heat exchanger, which is called an economizer, within the refrigerant cycle. So by utilizing a bypass valve, the hot refrigerant vapor on the condenser is bypassed through a heat exchanger, which combines with the colder gas on the evaporator expansion side. So the heat energy is transferred, raising the gas temperature even further, which then injects mid-range pressure into the head of this compressor. So we're taking that hot fluid, hot gas, injecting it into the head of that compressor to gain capacity. So you will, with this technology, you'll gain about 20% more capacity at a lower temperature, giving us that heat that is needed, okay? And we'll go through that a little bit more through the presentation. So this product is designed at a low ambient performance down to minus 20 degrees. And I'm going to show you some charts as we go through this that shows, yes, it can heat at minus 20, but what kind of BTUs are you getting out, what type of water temperature you're getting out, and how do we design around that. Same thing with the delivered water temp. Yes, we can go up to 140 degree water with this, but it also is going to depend on the system, the environment around it, and how do we achieve that. Has a user-friendly touch screen, so I'll show you a little bit on that. No refrigerant handling, and just to keep it simple, I mean, these heat pumps are basically like buying a refrigerator. They're already pre-charged. We're going to give them power. We're going to pipe them up accordingly, and they're going to work. So there is no refrigerant handling. There's no charging. There's no pulling vacuums, anything like that. Easily piped and zoned, you know, basically like a boiler, and built-in redundancy. So I'll get into that too as we get through this presentation. So here on the, so ultra low ambient temperature, like I already said, so it's designed for lower ambient areas, but also work in Florida, California, areas of that nature as well. You actually get probably more heat capacity out of it the warmer it is. And again, I'll show you that. That water temp at 140, and then we'll just touch on multiple use. So, I mean, it can be applied anywhere. It's basically just trying to match that load. So it's going to depend on how many you will need, but hotels, hospitals, expedition or exhibit centers, and we can also tie in a boiler as backup. And I'm going to touch on that as well, but just think of these areas where they're saying, I have to reduce the carbon footprint. But does that mean you have to take the boiler out? No, that means we may add 2 or 3 heat pumps, and all of a sudden we're reducing that carbon emissions. Okay, so just keep that in mind as well. That doesn't mean we have to go all in, all heat pump. We may still want to use some high efficiency gas-fired boilers. So here is just kind of a breakout of it. So it's a high efficiency. Our fans on there are EC motors, so they're going to ramp up, ramp down based on the ambient temperature. And we use an actual fan, which what that does is it brings the airflow straight up the shaft and outside, and then blows out the way the fan blades are rotating. If I explain that okay, but so on the larger surface area, so the bigger the coil outside, the more transfer we can get. We know that with high efficiency boilers or even cast iron boilers, the more surface area we have, the more transfer we're going to have. So that is why these coils are large, trying to gain as much transfer as you can. Vertical drain, so when it is in heating mode and or around that dew point, you are going to ice up on the coil. We are going to have to go into defrost, and that condensate is going to have to go somewhere. So it's a heated drain pan under the coil, and then we have that vertical drain, so the water will flow out immediately, so we don't have anything backing up. And then the compressors are sealed in a cabinet below the coils, pretty wide open in there. You can see a lot of things. And then here, okay, just to give you an idea of the working range, and again, I'll show you some charts as we get through this, but the heating ambient temperature is minus 20 to basically 110 degree Fahrenheit. And your cooling ambient out of the gate, minimum would be 59 degrees out up to 113. On that low end of 59, so let's say you had a situation where you needed to do cooling all year round, you would contact us, and there is some parameter change, and we can get down to 5 degrees. So if you had to do cooling down to 5 degrees, we can adapt to that, okay? On the efficiency side, when it comes to heat pumps, everything's driven off of COP, which I'll explain what that is on the next slide. But this other particular rating here, that IPLV, which is an integrated part load value. So because it is an inverter compressor modulating just like a high turn down boiler, they look at those inner parts of that load and calculate the efficiency as a total. Okay. On this product, as you guys can see, there's 2 fans. It appears like it's 2 coils and then 2 boxes. So they're separate modules. So let's just say you had one compressor fail, the other one would still operate. So there is built-in redundancy on this product. And now that I'm just talking about that compressor, there's 2 15-horse compressors on this product, independent refrigeration circuits. Okay. So again, to just touch on that COP, coefficients of performance, to keep this kind of simple, I'm just going to explain it like this. If I spent $1 for electricity and I just had resistant baseboard, let's just say, I'm going to get $1 of heat out of it. Well, now if I use an air to water heat pump or any air source heat pump, if I spend $1, I could get up to $3 worth of heat out of it. Okay, so that's how we're doing that. We're taking that energy out of the air, we're putting it into the refrigerant. We are using electricity to deliver this, but we're getting more bang for our buck by using a product like this. So getting into specifications, and I don't necessarily going to go through every one of them, but just to give you an idea, capacity range is from basically 100,000 BTUs up to about 290,000 BTUs. Your KW range 13 to about 28, COP up to 3.4. What else can I tell you on this? So if I'm looking at amp draw, so our amp draw is about 60 amps, and then our MOPD would have to be a 70 amp breaker on that. Oops, sorry about that. And then, so as far as voltage go, there's only one voltage option on this product, so it's 460 3-phase, 60 hertz. On the pressure drop side, so at 75 GPM, our head pressure is about 23 feet ahead, 10 PSI. So when we're sizing our pumps, we're going to look at that GPM, look at the head pressure, add our piping, and we're going to size our pump accordingly. Okay, but that being said, I just want to get into our minimum flow and our maximum flow. Because it is an inverter compressor, we can ramp down the flow rate, and we can also ramp the flow rate up. So our minimum flow would be 44 GPM. Our maximum flow would be 75 GPM per unit. Okay, so getting into heating capacities, right? So at this particular slide, I'm showing you the range at 100-degree Fahrenheit outlet water. Okay, so if we look at our capacities BTUs over here on the left, and then on the bottom, I'm showing you ambient temp in Fahrenheit. And then each one of these lines, blue being 90 hertz, so that's max speed on the compressor. And then this orangish yellow is a 60 hertz, so that's mid-range. And then the gray being 30 hertz at the low, call it low fire, low speed. Okay, so at 100-degree water, just to keep this simple, we'll look at the 30 hertz at minus 20 degrees. We're going to get about 50,000 BTUs. If we ramp up to high speed, 90 hertz, we're going to be somewhere around 150,000 BTUs at minus 20 degrees. So if we follow this thing up, and let's say it's 40 degrees outside, here we are, we're getting close to 300,000 BTUs at 100-degree outlet water temp at 90 hertz. And I think you get the point on the other part of the lines here. So just keep this in mind, that's 100-degree water. As I move into this one, this is the same type of chart, but now we're showing you it at 120-degree water outlet. And what is the difference here? So our capacities will drop off because now we're putting out hotter water. The compressors are working harder, but not a ton here at 120. So at minus 20 degrees, again, at that low speed, 30 hertz, we're somewhere around 50,000 BTUs. We're a little bit lower. And then the same thing at that high speed at 90 hertz, we're a little below that 150,000 BTUs at that minus 20. And then if we just look over here at that 40 degrees again, upwards of, let's just call it 260,000 BTUs at high speed and close to 100,000 BTUs at low speed. So now we'll move into 140 degree outlet water. So there is a price that you'll pay if you need to put out higher temps like this. And this chart here, yes, we can still heat down to minus 20, but the BTUs are going to be very low at that point. But let's just look at 0 degrees outside, 140 degree water. At high speed, we're putting out about 148,000 BTUs. So the reason I'm showing these charts to you guys, and this is all in our submittal data as well, is when we're designing a system and we know after we do our load calcs and have the bin data on that particular area, we just want to make sure we're sizing these things accordingly for worst case situations. And if we don't want to size them for worst case, let's just say I want to run this heat pump down to 20 degrees outside, and anything below that, I want a boiler to kick in. You can do that as well to try to get your maximum efficiency and the water temps you need coming out. So just to give you some dimensions on this, okay, so it's 86 inches long, 46 inches wide, and 84 inches high, okay? And our flange connections there on the water side are 4-inch flanges, okay? So getting into a shell and tube heat exchanger, just to kind of give you an idea. So you'll see on the right here, this right picture, we have our compressors, we have the refrigerant piping, and then we have this white cylinder, which is where the shell and tube is, okay? And I'll show you that broken up right here, okay? So a shell and tube heat exchanger is basically like a flooded evaporator coil. This is where your phase change happens with the refrigerant. But to explain it a little better, you have these copper tubes coiled up here. Inside the copper is where your water runs. Outside the copper is where your phase change happens. So we're flooding that evaporator coil, and we're flashing off, and we're making our transfer energy from refrigerant to water through this coil. On top of that, we have electronic expansion valves, so EEVs. So the reason for electronic is really because you have an inverter compressor that is modulating. So we also need TXV expansion valve to modulate with it accordingly. Your standard expansion valves, TXVs, are typically wax and spring driven based on temperature. These are really driving based off temperatures that they're reading from each part of the refrigeration system and adjusting accordingly. Okay, so this will improve your capacities by 10%, because again, we're trying to match exactly what the refrigerant is doing and how much we're going to let go out to our coil. Okay, so on top of that, it's going to give you a precision subcooling control at low temperature. So it's going to self-adjust to make sure we have proper subcooling throughout the whole time it's running. On the modulating side, so I've been selling heat pumps a long time. I used to work for our Space Pack division, so I've been through the on-off ones, I've been through the inverter ones, I've been through the two-stage ones, and based on what I've seen out there, when you have on-off, water volume becomes a huge part of the factor of how this thing is going to operate. So just think of a small loop, primary, secondary. You would absolutely need a buffer tank on an on-off unit, or you'll end up with curves like you're seeing here. So your purple line here is an on-off unit. So as it hits temp, it shuts off, and then it goes through its offset, and then it comes right back on and overshoots and does the same thing. With an inverter, just like a modulating boiler, we want to keep this thing running, and we want to maintain the temperature needed. So you're just kind of seeing a nice straight kind of curved line instead of these up and downs, okay? Same thing on the right here. So as we're looking at it, what's our capacity? We have a nice straight line versus, you know, a line that's up and down here. So it's a huge benefit to have the inverter so we can match the load needed and maintain water temperature. So same thing here. It's just another type chart. You're looking at your inverter heat pump and how our line is staying basically straight and we're maintaining temperatures. And your general heat pump on off, you are definitely going to have fluctuations in water temp. Here, I just want to touch on, because we are an inverter compressor, we have EC and fans, we really can keep these things somewhat quiet out there throughout the operation. So we can go as low as 56 dB at 3 feet. And if you look over at this chart, it doesn't really change that much. So if you look at the bottom, you have your low demand, low noise, right? So we have our compressor and low fan speed, low compressor speed, and that falls right into that 56 dB. As we ramp up the high speed, so we have a high demand, compressors are going to ramp up, fan speeds are going to ramp up, and we'll get somewhere up to about 70 dB there. So as it works harder, it can get a little bit louder, but still pretty smooth operating product on that side of things. I have, I've witnessed some of the on-offs, especially with a reversing valve involved, and you'll get a loud noise on the transfer of that refrigerant because your pressures are so high. And this being a nice soft start, along with the compressor and fans, your noise and transfer is not noticeable. So smart defrost, okay? So again, when we're in heating, there's potential of going into defrost. Typically, you know, 40 degrees down to 0 degrees. As we get to 0, that moisture in the air is not existent as much, so you may not go into defrost as much. So what I've seen out there in the past is defrost could happen on a timer. So basically, you're in heating mode, and every 60 minutes it goes into defrost. Well, that's no good, because if you go into defrost, you are now delivering cold water versus hot water. And we have to make that up, whether it is an electric backup or a gas-fired boiler, to keep that temperature going. So with our product and the way it's been designed now is we use pressure. All right, so we're looking at high pressure and low pressure. So as that coil starts to block up because of the icing, pressure is going to go up. We're going to kick ourselves into defrost, pressure will go down, we'll go back into normal operation, and it's a smoother transfer as far as the defrost goes. So just to give you another little idea how that looks, because we are independent, two modulars independent, I could have one in defrost and one in heating. And that's the way it's going to work, is the fact that, okay, we need to go into defrost. Let's do one coil, get it defrost. And this will happen in a matter of seconds, how quick they will defrost. Have that one switch over to heating, go into the next one, and put that one in defrost. So we're not completely out if we don't have some type of backup to inject warm water into the loop when we are in heating. And then the energy management. So as we're staging, so let's say we have multiple units up there, we're staging, I got one unit running at 50% capacity on each module, and then I have another unit that one module is off, the other one's running 100%. So it's always looking to try to match that load based on delivered water temp, and it will stage accordingly. So control board cooling, I think a lot of you, if not, I'll explain it, but you're used to VFD motors and how temperature really can affect how they work. So let's just say we're in a boiler room, I got a VFD there. If it overheated, it would stop working. That's why they have cooling fans on there. Well, with this, we took it and we added basically a small heat exchanger into that DC driven board, and that is keeping the temperature in there. So we're making sure if it's super hot out, we're still keeping it nice and cool on that control so it never overheats and we don't have any issues. So I find it to be a really cool design that was added, just to protect the board and make sure it never overheats. So on the control board, I'm not going to get into everything on here, but I will tell you this, it's pretty impressive that ever one of these lower inputs, whether they're sensors, pressure switches, whatever they are labeled. So let's just say we did have a bad pressure switch. It comes up on the board as a fault. We're able to look at that fault and say, oh, okay, it's inlet water temp. It's going to have that labeled on that wire, so you're able to trace it right back to where it is. So it makes it pretty simple on that side of troubleshooting. But the main focus, I wanted to just give you a kind of zoomed in look here where the power supply is. And one thing to keep in mind is it is three-phase, so you're going to have your three legs of power, L1, L2, L3. We want you to run a neutral as well and a ground. The reason for the neutral is if there's any components that are going to run off 120, like for instance, we'll send 120 to a step-down transformer, we need to have that neutral there. Also, if you're wiring a pump back to this unit, we got to have that neutral if it's going to run off 120 volts. Now, if we look down to the bottom here, we'll see that we have 220 volt electric heat. So we do have an output to kick on electric heat. I could also see this output being used to kick out a backup boiler with some type of relay there. Next would be 3 and 4, which would be your circulator pump out. So if we're doing dedicated pumps on this heat pump, we're going to use that to power our pump. And then 5 and 6 will give you an alarm. So if we need to turn a light on or some type of alarm, we can do that. And then moving over to 7 and 8, that's your flow switch. So it's not going to run if the flow's not there. 9 and 10 is our overheat protection. And then 11 and 12 is your remote on-off, excuse me. So that there would be, you would take a dry contact and you would either close it or open it if you want it on or off. Now, if we're using BMS, you just leave it closed and BMS would control it from there. Now over to 13, 14, that's your remote heat cool. That also could stay, I believe it can stay jumped or we keep it open, but regardless, that's how we put it in heating or cooling. And then if we look over at 15, 16, where you guys see that 485A plus and then 485B minus, that's where your Modbus connection would be. I'm not going to get too much into it, but there is a ton. If you look at our IOM, which we will send you, there's a lot of read writes, and it can do a lot of things. So just kind of look through that after, but for this presentation, I'm not going to dive too deep into that. The control, just to give you an idea of what the touchscreen looks like. So if we look at number 1, that's press the switch on and off, right? So power, we're going to hit it and power it up. 2 is your set point. So if we want to change our set points on this product, whether, again, if you're going to go 140 or you want to go 120 or 100 or even lower, same on the cooling side, deciding on what you want for delivered temp, that can be adjusted. And then 3, if you needed to do a manual override, you would press that to get it in cooling or press it again to get it in heating type thing. 4 is your lock and the passcode is 22. So as you hit that lock button, you're going to put your passcode in there, and then you'll be able to adjust some of the parameters, not all the parameters. If we have to dive deeper on things, that's when you would pull in our tech support. 5 is your timer. So how long do you want it to run? There is a timer mode in this thing. Again, that's in the IOM if you want to dig a little deeper, but you literally could keep the thing jumped out and just say, I want to maintain a loop and I want it to run at peak time or not peak times and things like that. So you can kind of adjust it that way. And then on 6 is your setting. So what do you, status, parameter, failure, time. So anything that we need to look at as far as that goes is there. Across the top here, so top right, you got 12. That's your ambient temperature. You have 13 there, which indicates your temp timer function if it is activated. 14 is an alarm. 15 indicates if it's in defrost. So you'll be able to see all these things so you're not questioning. 16, if you did have an auxiliary electric heat or again, boiler or some type of backup heat, it would let you know if it energized that to have that happen. 17, again, is your timer. So it indicates the power timer mode is activated. So if we were using the timer, it would say that it's activated, whether it's timed out or timed in. Indicate the lock screen, that's 18. So if the screen is locked, let's say you're a service contractor, you don't want anybody messing with it, you lock the screen, that will tell you. And then 19 is your fault. So if we had a fault, 19 would light up with that exclamation point, and then we would look and see what is that fault code and kind of tackle it from there. So application, again, I mean, we're looking to put this anywhere we can. So light commercial, hotels, schools, residential housing. I could even see some big type mansion homes maybe using one of these if they're doing inflow radiant, some kind of hydronic cooling at that point. If you look over to the right, this is just a kind of a clip of a project that we saw with multiple. I don't know if we'll do that here, but that's a lot of units up there. But again, this is the way things are moving. So if we have high BTU loads, we would need multiple units. So just to give you a couple of clips out of the IOM, I just wanted to show you if we're doing multiple units, we'd want to pipe reverse return. There is some limitations on how close we can put these together because we have to make sure they're getting enough airflow through them so we have no issues there. We don't want any dead spots on the coil that is not getting any airflow, so we're just trying to maximize efficiency. But as I said, reverse return, multiple units there. Over to the right side is just a typical piping diagram, whether it's a primary, secondary, or variable flow, whatever it is there, it's just giving you an idea of how we want it. We always want to make sure we're pumping to our highest pressure drop, and that would be that shell and tube heat exchanger. So we're always pumping towards the unit, not away from the unit. Just a couple other little piping diagrams here. So over to the left here is your reverse return recommended if we're doing multiple units. This one is one pump feeding multiple units, whether it's variable prime or not. There will be limitations if we were tying this into a variable prime system. Like I said, minimum flow of 44, maximum flow of 75 GPM. We really can't deviate from that. So just keep that in mind too if you're designing a type of variable flow system on the minimum flow rates. And then over to the right is your typical multiple heat pump, again, piped reverse return. But on this one, we have dedicated pumps to each one of the heat pumps. And then we're primary, secondary, so then we're feeding into the main loop of the system. And then I just wanted to show this one last one is basically a primary, secondary. In this particular one, we got one heat pump pumping towards that. But then we have tied in a boiler, whether it's an injection loop or just a backup boiler, or even an existing boiler plant that's there. We're looking to just tee in our heat pump onto that main loop and do what's needed there to reduce the carbon footprint. So pros of this air-to-water heat pump, it's 18 tons in cooling, up to 325,000 BTUs in heating. That EVI inverter compressor, which increases your capacity up to 20%. We have that touchscreen control. We have BMS communication through Modbus, and what I believe to be price competitive out there, but we'll see as we move forward. And then lastly, guys, I want to touch on one thing. So currently we're in development and we pretty much have a functional tool right now. If you were to bring us a project that you just needed to reduce the carbon footprint or looking at how do I do that, if you gave us the information on the loads on your project, what's there, do you want to integrate boilers and heat pumps, we can run that for you and actually tell you how much we can reduce the carbon footprint in that particular area. All right, so most importantly on this presentation, I want you to write down this pre-sales support, mainly the email here. So if you think you have a project that something like this would fit, send it over to these guys and they'll vet it out and let you know what we can and cannot do. But I think it's a good way to start us moving in this direction is have my team look at it, let you know where we need to go with it, and then go from there. So on top of that, if we have installed product, and this goes for boilers or the heat pump, you have this phone number here, and then you have the tech service email, and then the HeatNet support, which will be coming with a multi staging control along with this product. We could reach out to these guys, and then on top of it, keep keep in mind the heat net support on our boiler side. So that's all I have right now. We will keep on expanding on this. I plan on having some type of application manual put together at some point. But again, please just bring your projects to my pre-sales team, and we'll work from there. We're looking forward to the opportunity on trying to, get into this carbon reduction environment and going from there. So thank you guys for your time. I'm not sure. Is there any questions that I need to answer? Let me just look. Oh, okay, so I'm not seeing anything there. So again, appreciate your guys' time, and reach out to us if you have any projects. Thank you very much.